So what better way to make the last lab, if you did it, which was the panacetin lab and the sodium benzoate lab, to blend in with the next one. And this one, which is what you're watching now, is going to concern salicylic acid. All right, so salicylic acid is a structure that we have introduced in a previous video on a completely different lab. And if you've not attempted that lab yet, it's okay, because you will eventually. Just keep that in mind. This salicylic acid structure has shown up at one point in time throughout the semester. So I want to take a look at the structure in a little more detail, and I want to take a couple of minutes and talk about some of the properties that are associated with it. So salicylic acid, like many of the structures that we have seen so far, really is going to take this shape of benzene. And we see this benzene core yet again all over, a six-membered ring with alternating double and single bonds all the way around the molecule. And off of this structure, we're going to see a bond that goes to a carbon, and a double bond that goes to an O, and then one that goes to OH. Now, keep that in mind every single time that I draw one of these. And if you see kind of an area where there's a kink, so let me change the color here so you can see that a little bit better. There, here, there's a point of connection, there's a connector, all the way around this ring. Those are understood to be carbons, right? Those are understood to be carbons. They are not drawn in organic chemistry. It's really a waste of our time. We just assume that people know what that is supposed to be. And a lot of times we take that for granted because some people do not. All right, and it's okay. So all of those are carbons. So there's salicylic acid. However, this is not complete. On this side, we see an OH group. Now, by definition, salicylic acid is an acid, and an acid basically is a proton donor, right? And a proton, remember, in general chemistry, is a hydrogen. That's all that it is. It's a positive charge. A proton is just a simple hydrogen, and that means that salicylic acid will give off a hydrogen if it is in the correct environment. What kind of environment is that? Well, something that's basic, that's going to basically give that hydrogen a home. But if it's not a basic environment, salicylic acid will keep that hydrogen and it will hold on to it until it's forced to give it away. All right, so salicylic acid is the name of the structure. This name was derived from the name of salix, S-A-L-I-X. And like we've said before in a previous video, but if you've not watched it yet, this salicylic acid originally came from the bark of the willow tree. So the bark of the willow tree was kind of important. Many, many moons ago, people would chew on the willow bark, and it would help their pain that they were having throughout the day. So there had to be something to it, and chemistry basically went in and stepped into play at least, and some of the laboratory workers discovered that it's the salicylic acid in the willow bark that is allowing this pain to go away for these people. So it was long used in Europe, it was used in China, it was used in ancient Egypt. All of these areas knew to chew on willow bark to get rid of their pain. This thing is labeled as a mono hydroxy benzoic acid. All right, so mono basically means one, right? The hydroxy portion, what does that mean? Well, hydroxy in chemistry is going to refer to the just OH group only, okay? So this means there's one OH group. Well, we can kind of see that. It's right here on that structure. Okay. Now you're probably saying, well, there's another OH group and it's up here at the top. So why isn't this a dihydroxybenzoic acid? Well, that's true. There is an OH there. But what you're going to find out in organic chemistry when you take that course is that there's many functional groups that are very similar, and this is one of them. So if OH is just by itself with nothing else other than a carbon, then it's called an alcohol group or the hydroxy group, all right? However, if the OH is attached to a carbon that has a double bond O, then this is called something completely different. This is a carboxylic acid. That's what that functional group is called. And a carboxylic acid has different properties than an alcohol. So that is what this name is referring to. Just the OH group. That's it. It's not referring to the carboxylic acid group. And then finally, benzoic, you can kind of see where that term is coming from. Benzoic basically means a ring structure, and there's the ring structure for benzene. And acid is just giving me an idea that this thing is going to spit off a hydrogen if it can. Now, salicylic acid is what we call a metabolite. A metabolite of acetyl salicylic acid. And again, we've looked at this structure in a previous video. So acetyl salicylic acid sounds kind of fancy, but if you've not done that lab yet, it's okay, because acetyl salicylic acid is just aspirin. That's all that it is. So what a metabolite means is that you will take an aspirin tablet and you swallow it, and when you swallow the aspirin tablet, it breaks down in your body, and it goes and it does its job that it's supposed to do. Well, when it breaks down in your system, it changes into different products, and we call those metabolites because your metabolism is kind of breaking down the drug into something completely different than what it was in the beginning. Okay, so we call those things metabolites. So salicylic acid is a metabolite of acetyl salicylic acid, meaning that when you take aspirin, eventually some of that does go to salicylic acid in the end. And we've already said, well, salicylic acid was kind of dangerous because it gave us stomach ulcers if we took too much of it. So there are hazards that are associated with chewing on willow bark, and that was one of them. But, you know, that's not the only thing that salicylic acid is used for. So there's some other properties, and what are some of those other properties? Well, number one, it causes the cells to shed quicker. Okay, so the reason that I'm mentioning that is because this works wonders for opening up pores in your skin, right? So imagine a clump of cells kind of sticking together, and imagine some glue that's holding them together. And that glue can stop up the cells. It can stop up these little pores that are there. Well, if I have something that can go in and open up those clogged pores, then all of a sudden it causes acne and dirty faces to go away. And that's why we see salicylic acid used in the cosmetic industry quite a bit. So it causes cells to shed, and that allows the pores to open up. So pores can open, and that's good news for you and me. All right. Number two, it can also kill bacteria. That's also good news, right? So if it kills bacteria, that means if there's any kind of stuff in that pore that would set up an infection, like a nasty, pussy acne spot or pimple, well, don't go be popping, because salicylic acid will eventually kill that bacteria for you. That's all that nasty yellow stuff is, dead bacteria. And finally, it does constrict pore diameters. So it makes them open, it cleans them out, it kills the bacteria, but it constricts the diameters, which will prevent future pimples from happening. So very often people will wash their face daily in a salicylic acid cleaner. And this could be something like Clearasil daily face wash or Neutrogena daily face wash, and it helps prevent all of these breakouts from happening. Number 4, salicylic acid is also found in shampoo, and especially in anti-dandruff shampoo. It treats dandruff, it prevents it from happening, it makes it go away. Very similar activities to unclogging pores and opening up vessels and cleaning out bacteria, that type of stuff. Salicylic acid is used in the shampoo and conditioner industry as well. Well, if it can kill bacteria and if it can get rid of nasty germy stuff, then why not use it in your food? And very often some companies will use salicylic acid as a food preservative. So that's not uncommon either. If you look on your ingredient label and you go through and you read all of those that are listed, you probably will find a food preservative in there somewhere. And one of those, if it's not benzoic acid, like in your very first lab experiment, it could be salicylic acid or a relation to salicylic acid that's present. The WHO, which stands for World Health Organization, so let me write that over to the side. WHO stands for World Health Organization. All right. The WHO has listed the salicylic acid as an essential medicine. So it does so much, and it's considered safe for the most part, that the WHO has really played a role in allowing salicylic acid to take a role in your life without any issues or without any problems. Okay? So this salicylic acid structure can be changed. We can make this more potent. We can make this weaker. So acetyl salicylic acid has went in and changed the structure to make it weaker, because salicylic acid is too powerful and potent most of the time to take on its own. So we weaken it down into an aspirin tablet and we let you swallow it that way. So that's a little bit of background about salicylic acid and the importance of salicylic acid itself. All right, so here's a picture of salicylic acid. I'm just going to kind of drag this over a little bit and enlarge it. So salicylic acid in its purest form is going to be kind of this whitish to yellowish crystal, and the crystals are very shiny, they're very long, they look like needles, or at least they should, and it has a very low solubility in water. So it does dissolve, don't get me wrong, but it's a little bit stubborn. So you have to work it a little bit in order to get it into solution if you use water as a solvent. The formula weight is 138.12 gram per mole, and the melting point is 158.6. All right, so those are some physical properties that you might need in order to get this lab completed. And if it's low solubility in water, the question is always, well, what does it dissolve in, right? What can I use to make it dissolve up a little bit better? So we're going to see that ether, benzene, chloroform, ethanol, carbon tetrachloride, ethanol, acetone, and toluene are very good solvents for the structure. Now, why am I telling you this? Because a lot of these are more non-polar in nature, right? Water is very polar. And if it's not going to dissolve in water, that should give you an idea that this structure is going to be non-polar, or more non-polar than polar at least, right? So if it's not going to dissolve in water, we need to increase the non-polarity of the solvent. And I need to bring things in more organic-y in nature. And those are your benzenes and your ethers and your toluenes. Ethanol, yeah, there's some polarity associated with it, but you know, it's got an organic piece to it as well. Those CH2s and CH3s that are present, those are non-polar. So there are some physical properties of salicylic acid. What about the extraction and preparation? So the first extraction happened in 1828, right? and it was isolated by a German chemist named Johann Buchner. And he didn't really call it salicylic acid at the time. They called it salicin. And salicin was a molecule that was treated the same way as salicylic acid because it was the same stuff. And they knew some really health benefits that were associated with this molecule. But willow bark's not the only place that you can get salicylic acid. So other natural sources of salicylic acid, well, they're listed right here on the screen for you. You're going to see blackberries and blueberries and cantaloupes and dates and grapes and apricots and green pepper and almonds and peanuts. All of those have some type of salicylic acid relationship to them, if not salicylic acid itself. And if you go back and you take a look at a lot of these face creams and a lot of these masks that people will sell to you in any type of store, you're going to see a lot of these fruit products that are used. So it's very often that you might see an almond face mask or an apricot face mask, things made out of cantaloupes or blackberries. Not only do they smell good, not only do people associate kind of being natural with the face creams with those, if they put those on the label, but they also have natural sources of salicylic acid, and that's what makes those products work. So salicylic acid can be made a number of different ways. I mean, there's tons of what we call mechanisms or reactions that are associated with them. And you're only going to attempt one of them because you're going to be making salicylic acid, right? And that means that you're going to have starting products in order to make it. So the focus here is the hydrolysis of aspirin or methyl salicylate, oil of wintergreen. And most of the time you will use a strong acid or a base in order for this to work out the way that you want it to work out. So in this lab, if I'm not mistaken, they will tell you to take oil of wintergreen, methyl salicylate, and they will make you undergo a reaction with it, and you will end up with salicylic acid in the very end. All right, so that's where I'm going to stop this video, and in the next one, we're going to pick up from there, and we're going to talk about this reaction mechanism. So what does the reaction look like, and what's the mechanism that's associated with how this thing works? So I'll see you then.